And we are back in the lab. Today on the bench we have two Type 284 pulse generators. This is mine that I've been having trouble with for quite some time. It's been fighting with me. This is one that just got delivered today. I was hoping to get some readings off of one to help me fix the other. If everything goes well, by the end of the video we may have two working pulse generators. This one I kind of know the story on. Everything's working on him except the important part, which is the high frequency square wave coming out with the 70 picosecond rise time. Right now I have these resistors, which I'll go into. These are part of the tunnel diode airline. This is an extremely goofy setup. They had to do a lot of pretty crazy things to get the 70 picosecond rise time to work right, so it's a little strange. This one, I've been told it doesn't power up. I haven't even opened the case yet, so I have no idea what we're going to get into. But I'm going to try to pull it apart and at least put some power to it and see if we can't get some magic smoke or reaction out of it. But I'll go into this airline in depth because I have to rebuild the one for this. So we'll take a look at that. And we will also take a look at the tunnel diode. Now the problem with these is the tunnel diodes are unobtainium. I did find a place I can source a new tunnel diode for them, but they're $285 a piece. So they are not inexpensive diodes if you need one. So hopefully that's not the case with any of these, but let's get this apart, take a look at the condition on the inside. It's a little dirty on the outside. See what it looks like inside, and then I'll make a quick modification to these. If you don't know about it, it'll allow you to hook one up if you don't have the official power cord for it. So it's not a bad modification, but I'll show you guys that here in a second. But let's get some power on this one and see if we can't make something happen. All right, let's take a look at the inside of this thing, see what we're getting into. Haven't even looked at this, so you and I are finding this out at the same time. Oh. That's unfortunate. That's very unfortunate. Alright, let me move this out of the way and give you guys a close-up as to... Oh. Yee. Yeah. This was not stored in a good spot. This is extremely dirty. Alright, let me show you some of what I'm looking at. Oh, judging by the serial numbers, this is a much older unit than the other one. The other, you can also tell by the circuit boards. This has a gold circuit board. This is actually one of the reasons why a lot of people like the old Tektronix gear, because there's a decent amount of gold on that board versus the newer style, which has the silver, the tinned board, not the gold conductor board. So look at some of the crust on the capacitors. This is going to need some cleaning. This one's furry. Right there. We've got... This cable bundle's got some junk in it. Corrosion on the circuit board, so... This guy's going to need some... TLC. This is... The camera doesn't pick this up very well, but this is real bad. You can rub that with a finger and... Let's see. Yeah. So, this needs some TLC for sure. The modification is to do that. This is the one I've had. This is the new one. This black shroud can come off. You just pop it off, and it'll leave the plug out here. And when you have that plug out, you can just plug a regular outlet into it. So let me do a little bit of cleaning on it. Pull that cap off, and then we'll apply some power to it and see what happens. Okay, I've done the modification. I've also done an extremely brief cleaning of the unit. So the way I have the lab configured is I have this connected to the current limited isolation supply and the isolation transformer. The variac is set to 118 volts on the output. I have one light bulb switched in, which will give me about a half an amp till current limit. I have the power meter watching the power, so I'll know how much voltage and everything it's getting. We'll just kick this over here. Let's see. We'll set this to 1 volt square waves at 10 microseconds. Turn on my scope. Plug that in. So that's pretty slow for this unit. Okay, scope's warmed up. We will get a waveform. We will left, DC. All right, so moment of truth. What do we have? We'll turn the power on. I'll turn the supply on. No way. No smoke. Let me move you guys to the scope. I have an output waveform. It's drawing 5 watts, which is right where it should be. I'll turn it up. Yep. All right, that's working. Let me get some cables. Let's see if the tunnel diode side is working. The one thing that I know about that I've noticed about this is the power lamp is burned out. It doesn't say it's on, but it's actually on. The tunnel diode is so fast in these that you can't trigger off the tunnel diode signal. You have to use the trigger out. So let me zoom out so you guys can see what I'm doing. I'm going to move this over. Okay, let's see if the tunnel diode actually fires up. That would be incredible if it did. It is. Even the tunnel diode's working. Let's fire up the Rigol here real quick. I'm going to look at this on the Rigol. The output is a little high for the tunnel diode. It's supposed to be... The tunnel diode's supposed to be 200 millivolts. 70 picosecond rise time into about 200 millivolts. And this is way high. Could just be overshoot on the scope. Let me get a faster scope started. Okay, no, it's saying that looks right. However, its rise time is abysmal. So that is not looking too hot. It's a nice step response, but it's real slow. The scope's reading a rise time of 170 nanoseconds. Alright, so it does look like we have some problems with the tunnel diode enclosure. However, we are getting some power up. So, I don't want to stress the tunnel diode too much, having that on for too long. But that is a great place to start. All right. Let's get some caps changed out and see what we can make happen on this guy. It'd be great to be able to bring both of these back. Okay, as you guys can see from the puddle on the bench, I've been spraying a lot of alcohol, trying to get this thing cleaned up. The rise time was very poor. I think the tunnel diode's firing. I haven't checked this tunnel diode on a curve tracer, so I don't know. But I kept getting a rise time. The rise time equivalent bandwidth was 2.1 megahertz, so it was absolutely abysmal bandwidth on everything that I checked. So not good. This is what I'm having problems with on the other unit. This resistor right here, this sits in the back of the airline. Let me see if I can get this on camera. It sits in this housing. This tail, it actually sits in there like this. So it falls in. Let's see if I can get this. And it sits in there like that and like that. Now that's laying on its side. Normally it's interfacing with this spot here on the back of the airline. This is the center conductor for the airline. It's spring-loaded on both contacts. I don't want to touch either one of those. This is actually in really good shape, and I'm going to wipe that down with some alcohol when I'm done to clean it. But so this resistor actually breaks down. The outer resistor is the back termination of the airline, and these two resistors are what's hiding inside that barrel. So there's 3 resistors right here, and going forward I should have about 660 ohms, and in the back termination I should have 54 at DC, because this is a 50 ohm terminator for 50 ohm impedance. However, in looking at this one, I don't know if the camera's going to show that very well. There is a lot of just crap built up on that resistor. So I'm going to clean the back side of this resistor, put some fresh solder on it. Then I'm going to see if I can't take a measurement and see if these resistors have floated out of value or not. I'm getting way too much voltage coming out of the pulsar on this one. Should be around 200 millivolts pulse. I'm getting about a volt. So way too much power coming out of it. So, but these are the spare parts. These 4 resistors are the spare parts that I need to fix the other airline. Maybe get a second one of these going. The problem is these 2 resistors have a very, very important, these 2 resistors, come on, focus, there we go. These 2 resistors have a critical dimension because they actually fit. There we go. So what you can see right here, focus, there we go, is those resistors actually fit inside of the back terminator. So the diameter is an incredibly critical dimension. That's what's actually holding me up from fixing the other one. Is I haven't found replacement resistors enough. The back terminator is okay, but I've confirmed that these 2 resistors are out of value. They're supposed to be 660 ohms. They read 720. So they're 5%. So they are out of spec. So I'm going to get the Kelvin clips, and I'm going to see what this one reads. If that may not be part of our bandwidth problem, why our pulse might be slow. Measuring these without breaking them is fun. Okay, so measuring the back termination, it's 54.2. That's expected. The front, 684. That is actually in spec. So that may just be a corrosion issue. Let me clean up that resistor, and let's see if we can get some fast pulses. All right, so our DigiKey got delivered. So we have some chip resistors. What are these? 390s and 270s, 5%, quarter watt, 1206 parts. Just so happens the 1206 parts will fit inside the resistor, the back termination resistor. This little guy right here. So let me get some stuff assembled, and then we'll take some measurements and see how we did. Okay, here's our two 1206 resistors soldered together with a tail soldered on it to interface with the back of the pulsar tube. I did check the fit looks long enough, so what I'm going to do, because this tail's long enough, I'm going to solder the front of this directly to the termination resistor, so it's all going to be the same joint, so there should be no lead inductance on there. But here's the back termination resistor. And they just, there's through the other side, they just barely fit. So everything fits. Come on, camera, focus. Everything fits real nice in the end of the termination resistor. So let me get that soldered together, and then we will do a final measurement before we reassemble the airline. Okay, moment of truth. Keep an eye on that scope. I'll flip this on, and we do have 119 volts. So we're on. Kick this over into the mode. And believe it or not, that actually doesn't look any better. We're still getting almost a volt, but it's a really slow. All right, let me try moving this up to the Rigel and see if we can dial this in so I can get a rise time measurement. Okay, here's where we're at. We still got the 284 on life support. This, I've got the older tunnel diode that I had put in. I was able to confirm that the tunnel diode in the new unit was blown completely open. I'll show you guys how I confirm that here in a little bit. So this is at least from the last time I checked, known good tunnel diode. And I'm kind of looking at the pulses as they're going into the enclosure. So here is what I'm getting out of the enclosure. And if I adjust that, if I adjust the bias, the tunnel diode will try to fire, but it's not quite getting it there. And on the Rigel up here, these are my tripper pulses. So the tripper pulses actually look okay. This is 100 nanoseconds per division. So the tripper pulses actually look all right. Nice short hits. But the tunnel diode still doesn't want to fire correctly. I did confirm that the airline is now at the correct resistance value, so we should have enough bias current going into the airline. I'll show you what happens when I adjust the bias up. So if I adjust the bias, I get the pulse, but we're at 50 millivolts division. There should be a much quicker step here. And this should be step and then flat. So the tunnel diode's not firing correctly. But that's with the bias all the way at the extreme. With the bias in the middle, we're about right here. Now, the last time I had this on the curve tracer, I did not put it on the curve tracer today, but the last time I had this diode on the curve tracer, this diode tested good, and nothing has happened to it since then. So I'm pretty sure this diode's okay, and we have a problem on the board. So I'm going to start looking at this board and see what's going on. Maybe we have a voltage problem. We're not getting enough drive. Maybe we have some leaky caps. I don't know yet. But when I find something out, I will bring you guys back. And after a bit of fighting with the airline, we have a functioning tunnel diode pulse. So this is what it should look like. There's a slight pulse in the beginning, the very fast step, flat level, and then comes down. Everything is nice and stable. I can move the cord around a little bit, but you can see just the environment will change it just a little bit. So I got to tighten everything up, make it all good, but good tunnel diode pulse, everything looks good. Now my problem is my fastest scope in the lab is only 500 megahertz. I can't validate this pulse. I did set it on the Rigol, do a rise time measurement with the Rigol. The pulse is rising at 2.3 nanoseconds on the Rigol, which is to be expected. That's not a bad pulse. That's the limits of the Rigol. So the Rigol is only 100 megahertz. So the 2.3, 2.5 nanosecond rise time, 100% expected, and the good result. 3.5 nanosecond rise time is 100 megahertz of analog bandwidth. So everything is working. This is the newer of the two. So it's got the rebuilt resistor network. I will go through what I had to do for the airline to get it working and go through there. I'm going to do some testing. I'm going to do a lot of testing on that other tunnel diode to see if it is blown open. If it's not blown open, you guys will have to let me know if you want me to try to get this other one to work. If the tunnel diode is blown open, I will need to source a tunnel diode for that. That is going to be unobtainium or very expensive. But we'll see what happens, and we'll see what we can do to work on it. But it's working. All right. Well, unfortunately, lightning doesn't strike twice. This tunnel diode is completely open. This one's blown up, so won't be able to bring this one back immediately. We'll have to figure it out. What I can do is I can discuss the airline, what I had to do to get it functioning in the other 284, which happens to be a much newer unit. This is a much earlier unit than this guy, but we're good to go. He's still off to the side. I've had it running now for a couple hours and hasn't even missed a beat. It's been running very well, but I'll show you the pulse shape here in a minute. So this is the incredibly high quality airline that goes into here. This housing actually is what comes out of this side of the 284. Positive is in the front, negative is in the back. So you have a negative square wave pulse comes this way, a positive square wave pulse because the tunnel diode sits right here. So a negative biasing square wave comes this way, a positive biasing square wave comes in this way to the positive side of the tunnel diode, and then the tripper pulse is set on these two pins. The negative tripper pulse is over here, the positive tripper pulse is over here. You can see they're off-centered just enough to put them on one or other side of the diode. The diode actually sits right in the middle of this enclosure. The tripper pulses, as you can see, because this one's clear, my other one's not clear, but that's okay. I actually like the way this looks. There's a, it doesn't go all the way through, there's a dielectric right there, that deep. So at the very back of the GR connector, there's a dielectric that is clear, which is nice. But you can see the tripper pulses come in on the side of the diode. They actually don't even make any connection to anything. That's by design. They sit in the enclosure, and as the square wave pulse comes in, it biases it positively and negatively right before IP, right before the diode wants to kick into its high power state. And the tripper pulse comes in and is just capacitively coupled, just kicks it over the edge, which that's when it gives you the very fast rise time and sends the pulse out the front connector, because you then have a pulse, negative going pulse moving back that way and a positive going pulse going this way, which is what that back terminator resistor's for. That's back here in that enclosure that I had to rebuild. It has those two biasing resistors inside it, and then it has the back terminator, the 50 ohm reverse termination for the transmission line in this housing. The 50 ohm termination on the front side is the 50 ohm terminator that you have the cable hooked up to. So it turns everything into a 50 ohm transmission line. And that's how one of those tunnel diode pulsar enclosures work. I had to clean this contact significantly. There was a little bit of corrosion on here, so once I had the resistor reassembled, I had to clean this, and I cleaned this, and I cleaned everything in here that I touched. So I made sure there was no finger oils or anything on this rail. But I also, the rail was kind of loose over time, and there's springs here, so this comes apart, and then this comes apart. There's a spring there. So I stretched the springs ever so gently just to shore up the connection and get a better connection, because I noticed it was with the way the wave shapes were looking earlier, it was the terminator was messing up, so it was going terminated, unterminated, terminated, unterminated. Just wiggling the back of the connection was enough to, just wiggling the connection back here was enough to cause the terminator to make and break contact. So tensioning those up gave it a better connection on the tunnel diode and a better connection on the back terminator resistor, and everything started working. So we'll take a look at the pulse real quick. I'll move you guys over to the Rigel. Here's the pulse. This is the trigger output pulse right here. Actually, I can move that back and forth by switching whether it's 75 nanoseconds or 5 nanoseconds before the pulse. So this real sharp square wave, it's rolled off in the back, where the fall time we don't really care about, but it's got this real sharp step response. If I zoom that out, or zoom that in, here's our pulse. I can actually get that to go off the screen. There's the pulse. That's what the switch on the bottom of the unit does. It just moves that pulse for the delay. So I'll turn off channel 3 for right now, because the 50 ohms is into channel 1. And we'll speed up the Rigel as fast as it'll go. And we're having a 2.7 nanosecond rise time. Nice and steep, and then flattens off. So I will be able to use this to do high frequency calibration on scopes, which is one of the main reasons for the 284. The predecessor to the 284, if you're looking for cal gear, don't buy that one. It used a wetted mercury switch to get the step response. That wetted mercury switch has a very limited lifetime on it. So it got a fast pulse response, but it's not for long-term use. The tunnel diodes are much better. They're a little more fragile, but they are more desirable for sure. The only other thing I've had to do with this unit is I replaced the 2 bolt caps at the bottom. So I did that a long time ago trying to get this work. This has been a very long restoration. Actually, I started this restoration before I even started YouTube, so this was a broke unit that was sitting on the shelf for a while. I had gotten the filters in, then the tunnel diode quit, and I got stuck at the resistor problem. I wasn't sure if it was the back terminator resistor or a few others, so glad it's working. But a nice, just almost vertical step response. So there we go. Thanks for stopping by the lab, taking a look at this Tektronix Type 284. This is this was the problem. These are those 2 resistors that we replaced with surface mount components. So this has been pulsing right along for a while, and everything looks good. I'm going to let it run, and I don't expect anything to happen at this point, but I'm going to let it run and just do a smoke test for it. But this guy's done. So we do check the comments regularly. If you guys have any comments, please leave them down below. We do read all of them. And if you have any suggestions, let me know. See you in the next video.